Okay, welcome everyone. Today we are very happy to have Kyeongsik Nam from Korea Advanced Institute of Science and Technology, and he's going to talk about spectral large deviations for sparse random matrices.
Yeah. Okay. So thank you for the introduction, and thanks. I really thank organizer for organizing this nice conference. And today I'll talk about the spectral large deviation for random matrices, which is very sparse. And this is based on the joint work with Shoshana Ganguly and Ella Hismayer at UC Berkeley. Yeah. So, okay, so this is a very basic random matrix series. So we consider the following reverse scattering matrix. So there's a scaling factor 1 over root 10, and we have a symmetric matrix whose entries are centered with centered mean and variance. And the classical and the important question here is to study the behavior of eigenvalues of this random matrix. And it is a classical, so classically it is known that some kind of universality principle holds in the sense that the spectral behavior of this random matrix does not depend on the precise entry distributions as the size of matrix tends to infinity. So this goes back to the celebrated work by Wigner. So there's a so-called semicircle law for the empirical spectral distribution. And if we focus on the edge, then it is shown that under wide conditions on the entry distribution, one can show that the largest eigenvalue is close to the edge of the semicircle law, which is 2. So this is exactly the typical behavior of the spectrums. And one can also think about the fluctuation behavior near the typical values. So there are many people studied this fluctuation. So the most famous fact is that the bulk of the eigenvalue follows the sine kernel fluctuation, and the edge eigenvalue follows the trace rhythm. And today's talk will be about the large division part. So typically large division means that, so what is the asymptotic property of the atypical event? And it is very well understood for some kind of linear functionals of IID random variables like this. So we have under certain conditions, we have this kind of exponential decay for the IID sum. But it is quite delicate to study this kind of large division questions for nonlinear functionals of IID random variables. So this is quite important because there are so many crucial questions which falls into the nonlinear functionals. For example, we can think about the number of subgraphs contained in the random graph, and also one can think about the eigenvalues of random matrices. And it is very obvious that these two functionals are highly nonlinear functions of IID random variables. So this is a bit digression, but I will very briefly talk about the number of subgraphs contained in the random graph, because this has been a very active research topic recently. So let's count the number of subgraphs contained in the Erdős random graph. So what is the large deviation for that? So can we study the large deviation probability? And for example, if the parameter P is fixed in the number of vertices N, then using some kind of graph limit theory, Cherry and Varadan studied the large deviation for the number of subgraphs. But this argument does not work when P varies in N. For example, if in the sparse regime, when P goes to 0, then we need a new kind of framework to study the large divisions. So it was developed by Cherry and Dembo, and they reduced the study of large divisions to certain not mean field type relational problem. And now let's go back to the spectrum of Wigner matrices. So for example, so there are several types of observable like empirical distribution, but let's focus on the largest eigenvalue, lambda 1. And so obviously in general, large division probability depends heavily on each entry distributions. So there is no universality. And in the case of Gaussian case, so if we think about the GOE where each entry is given by Gaussian, then there's a very explicit formula for the eigenvalue distribution. So using such explicit formula, Benaro-Stenbo and Guillaume deduced the large deviation principle for the largest eigenvalue in the case of Gaussian case. But it took a long time to extend this to the non-integrable case. For example, if we think, so what happens if we think about this kind of general entries of the Wigner matrix? And Fanny showed that if alpha is less than 2, so this means that it is heavy case, right? So Gaussian case corresponds to alpha equals 2. And Fanny showed that if alpha is less than 2 in the sense that entry is heavier than Gaussian tail, then the large deviation speed is n to the alpha over 2, which is greater than n. And we have a certain rate function. But some interesting thing happens in the case alpha is greater than 2. Yeah, alpha is greater than 2. So I'll divide this into two parts. So this is also mentioned in the Nicolas talk yesterday. So first, Guillaume and Hugo show that if entries have some kind of sharp sub-Gaussian tails, then some kind of very surprising thing happens in the sense that the large deviation rate function is universal. So speed becomes n, and surprisingly, the rate function is universal, and it is equal to the Gaussian case. And in general, sub-Gaussian tails, so this means that it can be a bit heavier than the sharp case. And in this case, it is universal for small delta, but it becomes non-universal for large delta. So Ajari, Guillaume, and Hugo showed that the rate function is universal only for some kind of small deviation. And this result, so this was further analyzed by Nicolas, Raphael, and Alice, as mentioned in yesterday's talk. So yeah, so this is a review of the large deviation in the case of Wigner matrix, in the standard Wigner matrix case. And now let's change the direction to the sparse case. So this is a model we are studying. So in general, the electrical networks are modeled by some random graph, like Rudelson graph with edge weights. And in reality, this is very sparse. So in reality, connectivity is local and network is in general sparse in reality. And its adjacency matrix can be regarded as the sparse version of the standard Wigner matrix. So here sparse means that in the random matrix, most of the entries are 0, and there are only few non-zero entries in the Wigner matrix. So this is called the sparse random matrix, which I'll define in the next slide. And of course, the studying eigenvalue is very important because, for example, the largest eigenvalue measures the spread of the information on the network. So anyway, so what is the sparse random matrix exactly? So it is given by this matrix. So what is this? So if we forget about the y part, then x part is corresponding to the standard Wigner matrix. And y is additional factor. So you can regard y as a sparsifying factor. So y is Bernoulli distribution. So this means that we put the entry x with probability p, but we put entry 0 with probability 1 minus p. So in particular, if p equals 1, then this matrix is just standard Wigner matrix, very classical Wigner matrix. But if p becomes very close to 0, then this matrix is very sparse in the sense that most of the entries are 0, and there are only few non-zero entries. And this has a network interpretation, as I mentioned before in the previous slide. So this matrix is exactly the adjacency matrix of the network. So you can regard y as a Rudelson graph with the connecting property p. And you can regard x, so x is a real valued number, right? So you can regard x as a edge weight induced on the edge of the Rudelson graph. And it turns out that there is so the spectrum of this random matrix highly depends on the value of the parameter p. So it turns out that dense behavior holds until p greater than 1 over n. Of course, there's some kind of complicated polylog factor, but let's ignore that. So this means that, so what I mean by dense behavior. So here, dense behavior means that convergence, so the empirical spectral distribution is roughly semicircular, and the largest eigenvalue is close to 2. So such kind of dense behavior holds when p decays to 0, but not very fast. So if p decays to 0 slowly than 1 over n up to polylog factor, then the aforementioned dense behavior holds. But this breaks down if p decays as fast as 1 over n, like this, constant over n. So in this case, so if p is constant over n, the eigenvalue behavior is not understood. For example, we don't know the typical behavior, so almost nothing was known in this case. So the spectral behaviors are not well understood when p decays very fast as 1 over n. But particular type of this sparse random matrix is well understood. So this kind of very particular type. So what I mean is unweighted case. So here unweighted means that there's no weight x on the irreducible graph. So adjacency matrix has only 0 and 1. In this case, so using some kind of random graph theory, one can easily deduce the typical behavior of the largest eigenvalue, for example. So Kirvelish and Stokov shows that the largest eigenvalue is either the maximum value of NP and square root of D1. So NP follows from the fact that, so if the connectivity property is P, then NP is the average degree. So NP comes from that kind of quantity. And square root of D1, so D1 is the largest degree of the random graph. So what does square root of D1 mean? So square root of the degree is exactly the largest eigenvalue of the graph induced by that vertex. So yeah, if we have a very large degree, so we have some edges connected to this. So square root of the degree of this vertex is exactly the largest eigenvalue of this kind of graph. So the second part, square root of D1, comes from this fact. So so these two factors are competing. So if P is slowly decaying, then NP wins. But if P decays very fast, like 1 over n, then the second factor wins. So if, for example, if P is constant over n, then the second factor wins. Therefore, lambda 1 becomes square root of D1. But one can easily compute that largest eigenvalue is for the log n over log n. So we get this answer. And very recently, the large deviation for lambda 1 has been studied in different regimes of P. So this was mentioned in yesterday's talk, but I will very briefly cover this. So if P decays slowly than n to the -1/2, then Cook, Denbo, and Bartoshevich Ganguly studied this problem. And for P between 1 over n and 1 over square root of n, of course, there's a polylog factor, but I will ignore that. In this intermediate regime, Anirban studied this problem. And finally, if P decays like constant over n, then these three people studied the large division. Yeah. Okay, so what is the goal of the talk? So I'll consider the sparse random matrix of sparsity 1 over n. So here, constant C is not important. So what happens if P decays like 1 over n? And as I mentioned before, all of the classical techniques to study Wigner matrix breaks down. And surprisingly, even the typical value is not known, except the case when entries are 0 or 1. In other words, unweighted irreducible graph. So in this particular case, something was known. So as I mentioned in the previous slide, something was known. But for general sparse random matrices, almost nothing was known. So even the typical behavior of the eigenvalue was not known before. So our goal is to study the largest eigenvalue of such sparse random matrix. So in particular, when P decays like constant over n. Okay, so let's consider the Gaussian case because Gaussian is the simplest random variable. So recently in the joint work with Sherchendu, we showed that, so we deduced the following large division. So if entries are Gaussian, and recall that sparsity is 1/n. So we show that the upper tail, so this quantity square root of 2 times log n will be the typical value. So we studied the corresponding upper tail probability and lower tail probability. And we show that upper tail is some kind of polynomial decay. And this kind of rate function is a bit complicated, which I didn't write, but one can explicitly define this rate function. And lower tail has this stretched exponential decay. And as a corollary, we can show that lambda 1 is square root of 2 log. And the interesting aspect of this corollary is that we could not directly deduce the typical behavior. So we first proved the large deviation, upper tail, and lower tail, and then we deduce as a corollary to deduce this typical value. So we could not find a simple way to directly study the typical value. So so this is a Gaussian case. And of course, it is very natural to extend this to the general entry distribution. So let's consider the light tail case. So light tail means that the exponent e power minus t to alpha. So alpha is greater than 2. So this corresponds this means that it is lighter than Gaussian. So so this is a bit complicated quantity, which turns out to be the typical behavior of the largest eigenvalue. But let's ignore this constant part. This is not important. So let's look at just this blue part. So it is roughly square root of log n up to polylog factor. So it is square root of log n. And we could show that the upper, so we could show that, upper tail large deviation decays like this. But surprisingly, if you look at this rate function, this does not depend on alpha. So we could show that the upper tail large deviation is universal in the sense that, so of course, typical behavior depends on alpha. So if alpha changes, then typical value also changes. But surprisingly, the large deviation rate function does not change. So this rate function is independent of alpha. So we could show that the large deviation rate function enjoys the universality when entries have lighter tail than Gaussian. And interestingly, this also covers this also formally covers the alpha equals infinity case. So what does this mean? Alpha equals infinity means that there's no tail. So this means that X is deterministic. Like, for example, we can regard this as the unweighted case. So there's no random weights on the edge. So this formally covers alpha equals infinity case. So for example, if you put alpha equals infinity here, then if you study the asymptotic of this quantity, this exactly matches with the Erdos-Renyi case with no weights on it. So in some sense, this is a generalization of the previously known Erdos-Renyi graph case. So this is a summary of the light tail edge weights on the Erdos-Renyi graph. And one can also think about the heavy tail case. So what happens if the random weights are heavier than Gaussian? And it turns out that this quantity log n to the 1 over alpha turns out to be the typical value, and we could show the large deviation. And it turns out that in the heavy tail case, the large deviation rate function depends on the value of alpha. So in contrast to the light case, in the heavy tail case, the large deviation rate function does depend on the entries distributions. So what makes the difference? So they are very different. So for example, both the typical behavior and large deviation rate functions are entirely different. For example, if we consider the light tail, then roughly typical behavior is square root of log n, and there is a universality for the rate function. But if we look at the heavy tail case, the exponent is different. So it is log n to the 1 over alpha. So typical behavior is different, and we also get very different type of rate function. So what makes the difference between light and heavy tail? So I'll briefly explain the intuition of this difference. Oh, sorry. So before talking about the difference, I'll make the following corollary. So as a consequence of the large deviation, we could prove the following we could deduce the typical behavior of the largest eigenvalue. So as I mentioned before, if entries have a light tail, then it looks like square root of log n. But if entries have a heavy tail, then it gets log n to the 1 over alpha. This means that there's a phase transition at alpha equals 2 in the, so like Gaussian case. So why do we have a transition at the Gaussian case? And what is the mechanism between these two cases? So what is the difference between them? So I'll briefly talk about that. So let's first consider the light phase case. So what is the governing mechanism for the largest eigenvalue? So it turns out that the governing mechanism is the very high degree vortex with very high value edge weights on it, like this. So this is called the star graph. So it turns out that to have a very large lambda 1, the optimal strategy is to have a very high degree vertex with very high edge weights on it. So note that in the case of this star graph, we know the precise formula for the largest eigenvalue. So if we have weights wi's, then the L2 norm is exactly the largest eigenvalue. So this is a very simple formula. So what is the governing mechanism? So this is the answer. So in the standard Riddhipratim graph, so yeah, if we focus on the vertices of degree gamma times log n over log n. So recall that this blue part, log n over log n, is the maximum degree of Riddhipratim graph, and there is an additional factor gamma. So if gamma equals 1, then there are typically order 1 many vertices. But if gamma decreases, then such vertices, so there are roughly n to the 1 minus gamma many vertices of this degree. So this is obtained as just standard first moment argument. And what happens for each star? So if we think about the star whose degree is gamma times log n over log n, so we have the formula for the lambda 1 on each star, but we have n to the 1 minus gamma many stars. So we can think about, so the maximum eigenvalue is roughly like this, right? So we have n to the 1 minus gamma many stars, and each star we have largest eigenvalue, and we pick the maximum. And there is a competition like this. So what happens if gamma becomes larger? So the advantage is that if gamma gets larger, then degree is larger. Therefore, the eigenvalue on each star becomes larger. However, the number of stars is decreasing if gamma is increasing. So and the opposite thing happens if gamma is decreasing. So there is some kind of competition between, energy entropy competition between the number of stars and lambda 1 of each star. So we need to optimize, so we need to balance this competition, and we need to choose the gamma which optimizes this kind of mechanism. So this is what exactly happens in the light case, but very different mechanism happens in the heavy tail case. So what happens? So in the case of heavy tail case, the star thing, so here star is no longer the optimal way to have very large lambda 1. It turns out that instead of star, having a clique is the optimal way to have very large lambda 1. So the governing mechanism is that we have a certain clique, we have a certain complete graph on the Riddhipratim graph, and all of the edges have very, very high. So this turns out to be the governing mechanism in the case of heavy tail case. So what is the large deviation rate function? So we have a polynomial decay, and there's some kind of very interesting phase transition. So in the sense that this rate function is non-differentiable function. So it is some kind of piecewise smooth function. So why do we have such kind of non-differentiability? So this is caused by the change of the clique size. So here, so we are planting a clique, and then we have some kind of high values on each edge, right? So depending on the size of this clique, the large deviation rate function becomes different. So this is a reason why the large deviation rate function is non-differentiable. So as the clique size changes, the optimal clique size changes, the rate function behaves very differently. So this is some kind of unexpected result in our paper. And also very different thing happens between Gaussian case and much more heavier case. So between alpha equals 2 and alpha less than 2. So alpha less than 2 means that tail is heavier than Gaussian, right? So in the particular case, Gaussian case, the rate function is this ray function has infinitely many non-differential points. But differently, if it is heavier, then non-differential points are only finitely many. So this means that in the Gaussian case, if delta becomes larger and larger, then the optimal way to have such scenario is that plant a very huge clique and then have high edge weights on it. However, such thing is no longer true in heavier case. In heavier case, it turns out that even for very large delta, planting a very big clique is no longer optimal. So that makes this kind of difference. So the underlying mechanism is quite different between the Gaussian case and much more heavier case. Here. Okay, so for last 20 minutes, I'll briefly talk about the proof. So the setting is that so P is 1/n, right? So here constancy is not important. So in this kind of very sparse regime, what is the eigenvalue? So we have edge weights on this erudition range graph. And we decompose the entry into two parts. So the first part is that weight is large, and second part is weight is small. Then we can ignore the second part because if edge weights are small, but we already know the bound for the erudition range graph. So we can, if we choose the threshold appropriately, then one can ignore the second part. And what happens to the first part? So this is the dominating part. So we just need to look at the first part. But if we have this kind of truncation, then we have some advantage in the sense that, so originally the sparsity is 1/n. But since we are doing a truncation, we have additional sparsity. So the additional sparsity happens from this fact, indicator that weight is greater than something, right? So this gives us additional sparsity, and this turns out to be helpful for us. So this kind of new random graph is much more sparse than the original case. So it turns out that this resulting erudition range graph is very sparse in the sense that all connected components are very small, and all connected components are very close to tree. So it has very simple type of combinatorial structure. So our goal is to bound the largest eigenvalue for such kind of very sparse random networks. So I'll talk about some of the general strategy. So let's think about the symmetric matrix. So this is the adjacency matrix of the network. So this is a real symmetric matrix. And we think about the L2 norm. So this is also called the Frobenius norm. So we think about the L2 norm of the matrix. And there is a very trivial bound for the largest eigenvalue. So it turns out that the largest eigenvalue is always bounded by the L2 norm. And this is because trace of A square is sum of square of eigenvalues. Therefore, we get this very simple inequality. But surprisingly, this inequality is never sharp. So in some cases, this can be improved. For example, if the network is bipartite graph, then this can be improved to lambda square is 1/2 times L2 norm of the matrix. So why do we have this? The reason is that in the case of bipartite graph, there is eigenvalue spectrum is symmetric. So if lambda is eigenvalue, then minus lambda is also eigenvalue. So there is a symmetry for the spectrum. Therefore, this allows us to improve this inequality. So lambda 1 equals minus lambda n. So if you plug this here, then we get this improvement. So this inequality says that for certain type of graphs, we can improve the trivial inequality for the largest eigenvalue. So the question is there a general type of this result? And we proved that. Yes, so can we improve this for general graph? So so this is what we do. We show that. So this is for very general graph. So if the largest clique contained in the graph has size k, then we can improve the trivial inequality to this. So the additional factor is k minus 1 over k. So this is the improvement of the trivial inequality. So in particular, in the bipartite case, so the largest clique in the bipartite graph is 2. So there is no triangle, right? So only edge is the largest clique. So k is equal to 2. So if you plug k equals 2 here, then you recover the previous inequality. Yeah. And this is sharp in the sense that, for example, if you pick the complete graph of size k and all the same edge weights, then this obtains the equality. So this is sharp. So I'll present a proof of this because proof is very simple. So proof is just 3 lines. So how do we prove this? So we have a variation formula for the largest eigenvalue. So for any symmetric matrix, we have such variation formula. Right? So this is quite famous. And applying the Holder inequality, we can bound this by L2 norm of these 2 parts. So this is exactly the L2 norm of the matrix. So we can forget about this. So we can consider, we just need to consider the first part. So how do we control this part? And this is a very classical fact. So it goes back to 1965. So it is very classical fact. And most cases show that if the maximum clique size contained in the graph is equal to k, then the maximum of this quantity is always k minus 1 over k. So this is very classical fact. And using this fact, we prove this. Yeah, so this is very simple argument to bound the largest eigenvalue in terms of L2 norm of the matrix. And interestingly, this bound heavily depends on the geometry of the random. So yeah, using this general tool, one can bound lambda 1. And further, we can establish the structural result. So what is the governing mechanism for the lambda 1 having very large value? So as I mentioned before, the optimal way to have this scenario is that there is certain kind of complete subgraph and very high edge weights on it. And it turns out that they are uniform. This is some kind of uniform. So the governing mechanism is that there is a clique with uniform edge weights on it. So this means that in the large deviation regime, so upper tail regime, there is a very strong kind of localization for the type eigenvector. And what is the clique size? So this can be determined by the following competition. So what happens if the clique size is large? Then there is a competition. So if clique size becomes larger, then the probability that the random graph contains clique is decreasing. But there's an advantage in the sense that if clique size is increasing, then lambda 1 on this clique is increasing. So considering this kind of 2 competing factor, we can determine the optimal clique size, which gives this kind of large division effect. And yeah, as I mentioned, so we bound the largest eigenvalue in terms of L2 norm of the matrix, right? But this can be extended to LP norm of the matrix. So we could prove that the previous L2 bound can be extended to LP bound. But the drawback is that, so yes, of course, this constant is very explicit, but we could not provide the precise form of this constant. But we could prove such kind of existence of this constant, and this is sharp. So one can upper bound the largest eigenvalue in terms of the LP norm of the matrix, and this bound depends on the geometry of the random graph. So it depends on the size of the largest clique contained in the random graph. Sorry, not random graph. This is deterministic statement. Okay, so far I discussed the upper tail, but I'll briefly mention the lower tail case. So in the lower tail case, we don't have a polynomial decay. Instead, we have a stretched exponential decay. So it has a faster than upper tail. And this is quite obvious because the governing mechanisms are quite different. So to have an upper tail deviation, we only need some kind of local change. For example, we can plant a clique or we can plant a star. But in order to have a lower tail event, we need more global change. So this makes this is the reason why we have some kind of more faster decay in the lower tail. Okay, so this conclusion of my talk. So as I mentioned before, we focus on the case when sparsity is decaying like 1 over n, because this is exactly the location where the universality breaks down. So the semicircle law does not hold and everything breaks down. And the classical arguments does not work. So even the typical behavior was not known. So we analyzed this case, the sparsity is 1 over n. So we studied the largest eigenvalue using some kind of spectral graph theory. And we show that the typical behavior becomes different at the Gaussian distribution. So there is a phase transition at Gaussian entity distribution. And surprisingly, large deviation rate function satisfies the universality in the light regime, but not in the heavy T regime. Yes, so this is my talk. So thank you very much.
Now, time for questions. Okay. Oh, okay.
Right. I was just wondering, so in the case where you have bounded weights,
Yeah.
centered bounded weights, can you say also something?
So which weights?
If the weights are bounded?
Yeah. Weights are not bounded, so so the weights are
Right, but if they are bounded, well, do you expect that?
The bounded weight case are very similar to the unweighted case. So that corresponds to roughly alpha equals infinity case. So I think that case is easier than our case.
Okay.
Yeah.
Okay, and in the case alpha equal 2, then this result holds for the Gaussian or also other distributions, which have the same kind of tail as Gaussian?
For any distribution with alpha equals 2, right? Yeah, for alpha equals 2, I believe alpha equals 2 has the same behavior as the particular Gaussian case. That's what I believe.
Yeah. Okay. Because the typical value when
typical value
is less than
you're
2.
right. Yeah, typical value becomes different. Sorry, yeah, you're right. Yeah, so what is the mechanism for this? So this is exactly the maximum of n many Gaussians. So if the constant in front of t square is different, then this constant becomes different. But we believe this very similar large division mechanism happens. Yeah.
Okay. Okay, thank you.
Yeah, thanks for your comment.
Any other questions? So I had a question. So on the next slide, and also like where you have the light tail and the heavy tail. So I saw that you have a bound on the upper tail, but later you also give some idea about the approximate values of lambda 1. So do you have any ideas about the lower tails?
Mechanisms are same. So to have so this is a mechanism, right? So star, So to have upper tail event, then the mechanism is that we have a this kind of star, right? And the similar thing happens for the lower tail. So but in that case, the value of the weights and the degrees are different, but we have a similar. All right.
Thank you.
Yeah, thank you.
Okay, so let's thank the speaker again, and we shall reconvene at 3:30.